Well, thank you everyone for joining us today. My name is Maura Chambers and I'm from Pachyderm. I'm joined by our wonderful partner, ixpantia, and Frans van Doom. Frans, you want to introduce yourself real quick?
Sure. My name is Frans van der Nee. I'm the Chief Data Officer at ixpantia, and I'm very happy to talk about, Pachyderm, something that I find really fun. I hope to convey some of that enthusiasm to you all today.
Awesome. And today's webinar is Processing Data at Scale with R and Pachyderm, as I'm sure you all know. We will actually be doing a live demo, or Frans will be doing a live demo of calculating the fastest path to the beach using Pachyderm and R. So I'll start off just by setting some context on what is Pachyderm for anyone who is new to the technology. So Pachyderm is one of the technologies that Frans will be using today in his demo. And Pachyderm was really invented to solve the unique challenges of data science. So for one, effective data science should be explainable, right? And so a big portion of our platform is data versioning so that you can use the same best practices as your code with version data. Then the second main part of our platform is containerized pipelines. And this allows you to do data science at scale. It allows you to do data science and manage petabytes of data and thousands of pipelines simultaneously. And then the third piece, bringing these all together, is that Pachyderm allows you to do data lineage and be able to instantly reconstruct any past output or decision. So it gives you true provenance and reproducibility. And we think of ourselves as kind of a lab assistant that's going along with you as you're doing all of your experiments and tracking all of it. So you can go back to previous versions of your work and, like in all data science or science at large, show how you got to a certain outcome. So ultimately, we're an end-to-end platform that combines data versioning, data pipelines to give you that end-to-end data lineage. And I'll pass it back over to Frans now for the demo. Thanks, guys. If you have any questions, put them in the Q&A and we'll get to them towards the end.
Thank you. And in fact, Maura, if there's any questions, please interrupt me. If we need to push it to the end, we will. Moira, if you can help me with the Q&A, I'm well aware of the chat, but that I may not see. So just mention that there's a question out there. The idea is that together we will play around a little bit with what we can do on Pachyderm and highlight some of the main features. So first off, I want to talk a little bit about the problem that we're trying to solve. So in general, when we're working with R, right, or with Python or with Julia, there's so many options that you have there. But in this example, we're going to work with R. By default, you will be working on a single thread. And that single thread will be one process, and there's a theoretical maximum of 8 terabytes of memory that you can use. It's theoretical because few of our machines have 8 terabytes yet. And so the limits will be on the amount of throughput of whatever computation you're doing. Now, an easy way to go beyond that is to use parallel computing. There's really good support for parallel computing in R with the futures package and with the PER. So there, in theory, we could, buy an i9 machine with 32 threads, or maybe the latest AMD with 128 threads. And usually the amount of RAM that we have is available on a really large workstation is somewhere between 128 and 2 terabytes of memory. Very few of us have that, in fact, because of the cost. And sometimes processes need to go beyond that even. So there's the next possibility, and that is to farm out whatever you're doing to a cluster, multiple machines that are bound together in a cluster. And there, in theory, we have, a limitless amount of CPU that we could use, a limitless amount of RAM. It's practically limitless. There's a limit to everything, but you can build very large clusters really fast. So if this is so, we need a way to actually do that. And the benefit is not only to be able to run our processes, but also the cost, right? If we want one of those 128 gigabyte machines with, many cores, we could buy that. But for the same price, we could buy, two machines for per hour, of that same size would cost about $404.53. Or if we want to divide that into many different nodes, many different virtual servers, it would still cost the same, only we would have more. Now, this phenomenon that, it's really the amount of compute that you're buying and the price doesn't vary with the configuration, is really useful when we want to scale up our analysis, because we can optimize for throughput without having to take into account any difference in cost that might have. Now, the other big benefit of farming out on a cluster is that if you have two machines and one topples over, it fails, then that probably would impact your analysis. So using preemptible machines is less likely. Preemptible means that you're buying surplus compute power on AWS or GCP or wherever, that they offer to you really cheap, but there's a catch. It may fail at any moment. If you're working on, for normal machine, that would be a problem. But if you have a cluster with 32, 64, 1,000 machines, one of those machines or many machines toppling over at any given point maybe is not so problematic, because that was what a cluster will adjust for. So suddenly, instead of having the equivalent of 4,000 hours for your big expensive machine, you now have the equivalent of near to 20,000 hours, which is 2.2 years running this 24/7. So that is a lot of compute power for the same price. In data science, this helps us to, to tackle bigger problems with at a lower cost. So with that, having made a case for the benefit of farming out compute tasks on a distributed in a distributed mode, let me explain a little bit how that actually works, right? For some of you, this may be very obvious, but then, I will start soon with a demo. It's just to make sure that we all have the same context. So these are pieces of data. In Pachyderm lingo, they're called datums, right? So a datum is a unit of data. It can be a JSON file, it can be a zip file with multiple JSON files, it can be anything. Each datum we want to process. We want to do something with it, and there will be a result. But very often, that result we want to use to do something else, and then we have another result. Very often, it might be there might be some aggregation steps. Sometimes there's not, but this is the example. What we can do now on the cluster is decide that something we want to run in parallel with many small VMs, because having more processing power is actually what will help to make it faster. But maybe in that last step, something else, we need to aggregate, and it is more useful to have one large machine to do that step with a lot of memory, because it's easier for us to write the code that way. Those decisions, to implement them on a cluster, are not so straightforward without tooling. Luckily, we do have tooling, so we can do this without, without much trouble, and that is what we will show you today, right? Are there any questions so far, or anything that I can clarify? No, good. So now for the technical demo. What we're going to do is, as Moira already said, we're going to figure out how to live closest to the beach in Costa Rica. And to do that, we need, of course, data from Costa Rica. And this demo was designed and implemented by my colleague, Patrick Santamaria. He understands geographical data very well. And we thought of something fun, and he came up with the example that I'm going to show you. So what you're seeing is a map of Costa Rica. In purple are all the beaches. So each beach has a name. It's a formal beach, right? So here, somewhere here is Playa, somewhere here I think is Playa Panama. There's, there's a lot of them. Costa Rica is divided geopolitically in 82 cantons. And each of those cantons is subdivided so that we have a total of 235 census segments. Those census segments is what you are seeing lined up here. So in the first step, we're going to divide a shapefile of Costa Rica into those 82 cantons so that we have 82 datums with each of them the census segment information. Then we're going to associate each of those segments to the closest beach and calculate the distance. Now, this example makes sense for us because if we zoom in to this little area here near Punta Arenas, calculating the distance between a polygon centroid and a beach, that is not so much of an issue. But doing it 235 times even takes a long time. And if we would want to go one level deeper in granularity, it would take even longer. So this is an ideal case of something that is easy to make embarrassingly parallel, which means that one calculation does not impact the other, right? So it's very easy to parallelize it and put more machines to work to actually get this done faster. So our computational steps, when we want to put this on Pachyderm, we will define in something called pipelines. I will show them to you in a minute, right? In this case, we have three. So Patrick thought about the problem that he was handling, and he figured out which were the three steps that made sense to separate, either because of their characteristics or because one step leads to new data that will feed the next pipeline, and so on and so forth. So in the first one, we separate the data that we have in the 82 separate shades for each canton in Costa Rica. In fact, what he's doing is he's joining a shapefile with the cantons with a shapefile with the census segments. Once we have that, we have 82 different shapes, and each of those now enter as a datum in the next pipeline. And there we will associate each segment with the closest beach. They'll calculate the distance to that beach in meters and then save the result in a spatial object for that canton. So there will be 82 objects, each with one or more census segments and the distance to the beach. And then in the last step, we aggregate, we join those 82 results into one file that we can then download and visualize, and that would be our result, right? So the steps that we go through are the same steps that you would go through for anything that you want to calculate in this fashion, right? First of all, we need to put that calculation in a Docker container and put that in a container registry. I will not go into that because it's sort of a separate topic. So we have the container ready-made there. I will show you some tips that we use when we have multiple steps and we want to optimize the way we work with containers. The second step is to get a cluster on the Pachyderm hub. You can run your own cluster, your own Kubernetes cluster, then install Pachyderm on top of that, especially if you want to have large clusters, or you can just use the managed service by Pachyderm, which is a lot easier, and I will show that to you right now. But please note that it can be done as well using the open source version, right? You have that freedom, and at some point, if you feel that a managed service makes more sense, you can go over to the Pachyderm service. We need to put our files in the Pachyderm repo in that initial repository and then create our pipelines, right? So this is what we're going to do. Oh, that is the end result. We're not there yet. So first of all, and that is in this screen, if you log into Pachyderm Hub, you will get this screen. I'm automatically logged in, so I always end up here when I go for Pachyderm Hub. But the address is as follows: it's hub.pachyderm.com. And as I said, I'm already logged in, so that is where you would end up, or that is where you register. You have the option to create a free 4-hour workspace, right? So for these kinds of experiments, that works really well. And when you do, you get a workspace name. You can change it if you wish. You need to agree to not put in any HIPAA-sensitive data or any personal PII is personal identifiable information, and we create the workspace. So far, so good. We then connect to this workspace because what we have now is a Kubernetes cluster with Pachyderm installed, right? That is all set up. It's ready for you to use. So when we connect, we actually have the steps for us here ready to copy paste into our command line. So I will run the following in my terminal. Then I will log in. And I need to put the one-time password, which is included here, and here we are. I can check now that I'm logged in running pachyctl version. And it will say is, okay, I'm running pachyctl version 1.12.3 and pacd 1.12.0. Right? I want to see what is happening, and I want to show you what will happen in the demo. So what we can use here is open the dash, the Pachyderm dashboard. And the Pachyderm dashboard will be a visual representation of what we will be doing on the command line. Everything that I'm doing on the command line actually, has a sort of interface equivalent in the Pachyderm hub, or maybe not everything, but many of those things. I just feel more comfortable in the command line, so that's why I'm using that, right? But there's no, if you want to experiment, there's a lot that you can do with the interface that the people at Pachyderm have built. Cool. So what we have as an example, I have here, right? Those are the files that I've prepared for the demo. What I will also do, and you will see me jumping between them, you see here it says local, and then I have another screen that says PackHub. And that is because I like to work with Pachyderm using the Pachyderm pachyctl, using Pachyderm shell. I'm in that shell right now, and that means that I can give the commands not only in a briefer fashion, but also I can use autocomplete, right? So we will create a first repo soon, but that is the big advantage of using Pachyderm shell, and you will see me using that. Before I continue, let me show you what we've done to set the stage. As I said, bringing out a preparing a Docker image is not part of this demo because most of you have done it before, and if not, there's a lot of documentation how to do that. But it does make sense to show you how what that Docker image looks like. So if we take a look under the hood at the Docker file, you will see that it is based on R because it's an R process that we're running. I have my dependencies on the system level. I have my dependencies on the R level. And what I've done is copied 3 separate scripts to that Docker image. Each of those scripts represents one of the steps in the pipeline. So what you will see in the pipelines is the following. If I open in the pipelines, let me show them to you first. So we have 3 pipelines that were defined, right? The one where we separate the files into different cantons, the 82 cantons, the one where we calculate the distances to the beach, and the final one where we're going to join the results into one file again, right? Let me look at the first one, because the first one is the one that where we're going to separate. So here we go. We take a look. And this is what a basic pipeline looks like. So we have a name. In this case, it's distances. We have a description. It takes a canton shape and calculates, that is, I wanted the first one, which is separate. Pipeline separate. Right. Take a shapeful with segments and separate into files with cantons. So it needs to find where that data is. And this reference, PFS, is the Pachyderm file system. It is the repo that I will create in a moment. And that repo I will call shapes because that is what the pipeline is referring to. Then in the transform, we are referencing to the image. It's a Docker image where the actual computational steps are defined. And in the command, see here, call the R script separate R. That way I can use one image and use it for the 3 different steps, because each step will have a different R file, R script that it is calling, right? The parallelism specifications can be much more extensive, because here we define how many parallel containers we want to run. We can even define the sizes, etc. But that is a little bit more advanced. So we will focus on the basic process first. Right? Okay. If we're good so far, then we're going to create that first repository that we call shapes. And we literally say create a repo, and we give it a name. We give it a name shapes. And look what happens here. I now have shapes coming up on the visual representation that we have online on the Pachyderm dashboard. I can also do that same thing here on the command line. I say list repo, and I have one repo that is called shapes, right? Cool. So now we need data inside those shapes, because if we look here, we have undefined data files. We don't have nothing yet. It's just the repository. So to do that, we need to do a put action, right? Insert the data into Pachyderm. We need to call it from elsewhere. What we have done is we've set up a bucket with example data, because that works really well. You could also put it from your local machine if you're so inclined, right? But in this case, we're going to put a file, many files, and we're going to put it into shapes. And look that we have to call shapes by saying in which branch we are actually working, because the way that Pachyderm organizes data is in repositories, hence the data versioning that we're able to do. So in this case, we go to the master branch and we say, okay, copy everything that is that you will find here in this bucket. So it's Pachyderm demo and the shapes folder. This will give an error. I could have solved this beforehand, but I'd like you to show this trick. If we want access to that bucket, we need to give the service account of this repo access to that bucket. So what I will do is I will copy this. I will go on GCP to my Pachyderm demo bucket, and I will just add one user and say, okay, this is an object viewer, and I will save. Policy was out of date. Okay. I've not seen it before. I hope I don't run into any issues. This way you can play with data that is yours without having to make it, open to everybody, but you can still keep it restricted. And if I run it now, it will actually start copying, and we should see that at some point reflected here. There we are, right? We copied 17 data files into one directory with a total of 32 megabytes. And we can see the shapes folder. And in that shapes folder, the files that we actually copied. Again, if we want to do that here, we can do the same thing. We can say list a file in shapes shapes master. In the shapes directory, and there we are. We see the same thing. Okay. Cool. Now we are ready to actually do something with the data. So we're going to launch a pipeline, or in Pachyderm, we're going to create the pipeline because it's not existing there. I make this a little bit smaller. In fact, I can close this so that we can see what actually happens. Remember that the pipelines, I have the pipelines, I have them here, right? So the first one we're going to do is the separate pipeline. We need to bring that over to Pachyderm because it's on my local machine now. And the way we do that is we say create. What we want to create is a pipeline, and we want to do that from a file. And the file's here. It's in pipelines, pipeline separate.json. It's now bringing it over to Pachyderm, and look what happens. There's my pipeline, separate shapes, and I can inspect it. The pipeline is the green arrow, and it's an arrow because it points to an output repository. The separate shapes pipeline has an output repository that at this moment has no data files yet because it's starting up. And we can see that it is starting up because it's not active here yet. But if we go on the command line, we could do this. We could say list the pipeline. And we have our separate shape pipeline that is starting up. And it gives the description, take a shapefile with segments, etc. We saw that before in the pipeline definition. Right? Once it is started, it will start a job, right? And let's see if that job is already there. List a job. No, it's not there because it's still starting, right? And actually, this might be the moment to say that if you, this will be much faster if you have a lot of data to process. But if you have just, one or a few files, anything that your local machine can handle, then just working on your local machine will be faster, right? You don't have to wait for things like we're waiting right now. Here, now it's running. And we see it here running as well. See, things are starting to move. There's 30 megabytes that it will start to process. And now I'm pretty sure that we will see a job. There it is. We can get the details of those jobs, right? If we say inspect job, thanks to shell, we can also complete. So we say 499, that is the job that we are looking at. And it will state what it is doing and how it was defined. But more interesting is the log, right? What if something goes wrong and I want to inspect what is happening? So if I want to do that, what I do is the following. I say inspect, logs, job is, I think I need to copy paste jobs, list. Right, we get the logs. For the, we inspect the job and we do that same job ID 499. No, that's not the one I want. I want the log. Oh. Oh, I don't have it there, sorry. Right, so I want logs, job. There we are, thank you. There we are, that's what I wanted to show. So what we have is the log of the actual output of the process, and we have 83 of them, right? With the last one is probably empty. But these are the steps that were taken in that particular job, and we can see that it is finished, right? We have no active jobs. And where we want to go to is in this repository, see what the output actually was. Let me refresh one moment. Because if we list the repos now, we now see two. We had a repo that was separate, the shapes that we created. Separate shape is the output repo for the pipeline separate shape. So the results that we have there are the 82 data files that we were looking for. These are the ones. These were created by this pipeline, right? So now we are ready for the next step. And we're going to create another repo, but now want to hold our beaches. I'm going to move this here again for us to see what is happening. And there we go. We say create repo, beaches. And lo and behold, there the beaches repo is created. We need one file here that has the beach information. So we will get that out of the result file, put that locally, and then upload it to the beaches repo, like so. So we get a file, and we get a file out of out of one of the repos that are there: separate shape, master, and whoop, There we are. It's in shape segmentos, and it's called, this is because I know it's there, and it's called Playas RDS. We want to save that in an output file as Playas RDS. There we go. So this is how you download to your local machine. I can show you that it's there now. There it is, Playas RDS. It wasn't there before, right? So now we're going to put this file in a separate repo. We're going to put file on beaches, master. It's a local file and it's called Playas, Playas RDS. Now just to show you what will happen, undefined repository, there's nothing there. We now put it on the cluster and hey, there it is, one data file. With this, we can now set up our next pipeline, right? Because now we're going to calculate distances. So we create another pipeline, distances.json. That won't be found. Pipelines, because it's in a local folder called pipelines. And there it goes. Now watch what happens. Beaches is placed in a separate position because what we are doing here is combine data that is in two different repos. As an example, this is an example of how you can work with data from different sources within Pachyderm, and I will show you what it looks like in the pipeline distances. Because the input here is a cross. There are different forms that you can do this, but this is a cross. So we're going to, for each of the datums that we have in Shake Segmentos, we're going to combine that with the RDS of Playas to make the calculation, right? And this is pretty cool if you have that need in very large data sets, because Pachyderm helps you out. While it is calculating, because this will take a little while, about 4 or 5 minutes, what we can already do is create the next pipeline, the one where we have to join. So we're going to create the pipeline, where we have the pipeline join.json. Note that it will be available now in our DAG, right? After distances, because that's how we defined it. But it will not do anything. It will not start until distances is complete, because one depends on the other. So if I now list my pipeline or my pipelines, I will have one that is running, and the last one, join segments, that is starting, but it's not starting yet. It will start when distances has been finalized, right? We need to wait a little bit on distances because it's an there's an active job there, distances, where the that will take a little while. And how long? We can check here online. We can see the number of datums that have processed, and we can see that here as well. Maybe if I make this a little bit inspect pipeline distances. It will say something about the number it is running. No, this is not where I want to be. What I want to show you is the equivalent on the command line of the number of jobs that we are going to see that have been processed, right? Because we have one active list. And probably the easiest way to do that is data distances. There's none found yet. It is still running, right? It's still starting up. So let's give it a little time to do that. Oh, there we are. 19 datums have been processed. Of the total. And they're not here yet. And we will see that increasing as we go along. So Jose Molina, as we wait for this process to finalize, Jose Molina asks, Everything you're doing with the command line, is there a way to define this all ahead of time in a YAML or something that can be checked and saved with the definition to be able to deploy a state or Pachyderm pipeline? Yes, right? So I'm doing this by hand to show how it works, but that definition of the pipelines that you can then upload in bulk is what we have done here in this folder, pipelines, right? So again, every step that we're taking here is defined in the pipeline distances, and once they're up and running, they will be listening, they will be watching out for new datums to come in to run again with the process, right? Which is what I was trying to, or what I am trying to show you with this example. Joint segments will not run until distances is complete. But then when there's new information coming in, it will go through the whole process again. Yeah. Good. Let me see on the other side how far we are. List pipeline. It's still running. Right. That is the one I was looking for. So list job. These are the jobs that are running. This is the interface I was looking for. So in the process for distances, it started 5 minutes ago. We have 61 of the datums already processed out of a total of 83. And there's one that seems to have run into a failure. We will see which one is that in a minute. Yeah. Okay. Any other questions as we wait for the last one? Oh, it's done. So I can now see that they all run with success because the last step was not so intensive. So that run immediately after the other one finished, it ended up with the joint segments. So if you now have a look at what is in that repo, list the file in the output repo for the pipeline joint segments, right? At master. Then we have our file segment as as RDS. This file we can now get to see if we actually got the full result. So let me get that file, get file. It will be in the joint segments, right? Master, the file applies RDS. Oh, I didn't specify the output name. Sorry for that. So let me repeat. Oh, and we will give it the name result .rds. Okay, there it is. And if we go for the final, we now have the result here. To show that result, I need a little bit of R code to make the visualization. So I have that here, and it's not in data. The result will actually be here in result RDS, which is what we called it. Let me check if that is okay. Yes. So we have some R code to map. I could not find a function because I didn't load anything yet. Let me load the required libraries. There we go. Let me repeat the visualization. Andres, I probably do something with tabs that I'm not even conscious about. So I'm not quite sure what you're referring to, but I'll be happy to explain how I work in, whenever. So this is the end result. And what we have here is an overview, a heat map of the vicinity to beaches. The good news is that, there's almost anywhere you can go in Costa Rica, you will be close to a beach. I actually live here, somewhere over here. So I'm close to the Caribbean and as close to the Pacific. But if you're planning your trip, this might be one way of doing it. If I get back to the presentation to finalize, right? These are the steps we've taken. We've created a pipeline. We finished up. with the end result. And in summary, the main thing, and I think this took us the longest when we first started out using Pachyderm, is that you need to understand that the Pachyderm file system is a thing, and you need to call it as such in your script. So if we call the directory Pachyderm file system distances, and then the directory Pachyderm file systems out, every pipeline, there will be a repo that you can access without, and it will write result files. If you have that, then the rest of the scripting is pretty straightforward, right? We could have done this on Kubernetes straight and simple, and maybe using Airflow or something like that. And we would have a bucket, we would farm that out in Kubernetes, have another bucket, farm that out, and have another bucket. But with Pachyderm, we have something different, right? The way I see it is that we have a filing cabinet. We have a drawer where we have our input files. Then we farm it out. There's another drawer where we have the first output files and then the end result somewhere else. It's labeled. I can go exactly where I want to go. And if I make a change, that change will be visible in each of those drawers. I will be able to see what was changed. And if there's an error or something else that I need to change in my pipelines, I will be able to follow the process as it went along during the execution of the pipelines. And that on top of the relatively straightforward way of defining the pipelines helps a lot. So with that, we go into the Q&A. The first question usually is, will you share the code? Well, yes, it is there on GitHub. Actually, it's here. Oh, so the 4 steps that we followed, step 1, step 2, step 3, with what you saw on screen, and all the R code that goes behind that is ready there for you, right? Any other questions? And Moira, please help me if I didn't see anything in the Q&A or somewhere else.
Yeah, great job, Franz. Thank you so much. So a few questions have come in and we've tried to answer them kind of along the way. But another one that came in through the chat that would be good to answer is, do you need to know R to use Pachyderm?
No, the beauty of Pachyderm is that it's completely language agnostic. So any process, even you can combine languages. Something that, for instance, you have something in R because it's you want to use the SF package and do something with spatial data. You then have a process in Julia because you really wanted to optimize it, make it run very fast. Then maybe a step in Python or whatever. As long as it runs in a container that accepts datums and outputs datums, Pachyderm will work for you.
Great, thanks. And then another question is, how does Pachyderm differ from another pipelining system like Kubeflow? And we also have Jimmy Whitaker on from Pachyderm.
I was going to pass this one to Jimmy. Jimmy, I think this one is for you.
Yeah, sure thing. So let's see. Sorry, what was the question again? I'm typing answers to another question.
No worries. Just how does Pachyderm differ from Kubeflow?
Yeah, so we get that one quite a bit. So Kubeflow is really it's almost a collection of tools more than anything else. So for instance, it's kind of trying to merge a lot of different open source projects into a machine learning kind of deployment on top of Kubernetes. So Kubeflow is typically more oriented around the experiment, create an artifact, and then deploy that artifact sort of process. But managing the data component is difficult or kind of separate from Kubeflow, except for maybe a couple tools here or there. And that's actually a key component of what Pachyderm does. So in my opinion, the main difference between Kubeflow and Pachyderm is really focused on this kind of immutable data first approach, so that pipelines can be reproducible at any state. And then you get a few benefits from this as well. So you can automatically run these pipelines when data changes, roll back to previous versions of this was my version of my data, this is my version of these pipelines. And you kind of have this this living system that you can always go back to previous states of it and those types of things aren't necessarily in Kubeflow natively. That being said, we've actually done some work with Kubeflow, and we've called it KF data to try to bring some of these data-driven concepts to Kubeflow itself. So if people are interested, we can link the KF data proposal and then some of the work that we've done to use Pachyderm as the data layer underneath Kubeflow.
Great, thanks. And then maybe let's answer these open ones live as well. So from Emilio, does Pachyderm work for big calculations within Shiny apps? How does scaling work?
So Shiny apps, for people who are not so well versed in R, Shiny is like the dashboarding interactive visualization package that we use in R, right? So Emilio, what you have there is two system components. You could very well set up, complex pipelines with Pachyderm that give you an end result. Maybe write out the data at the end to a database that then feeds your interactive visualization within Shiny apps. Conceivably, you could start and stop things within Shiny apps if you so wish, but that is something that we haven't done yet. But your visualization and your data pipelining are two separate components. And yes, you can link them when you need. You need to think a little bit about what makes most sense in your use case, right? Does that answer your question? Okay. Great.
And then maybe let's address Ashar's question live as well. So would it be fair to refer to Pachyderm more as data pipelines, as the R file, which transforms the data, is something which is not tracked in a systematic way in Pachyderm? I'm thinking of ML ops, which especially take into account the changes in R Python code. Jimmy, I know you answered that over text, but you want to speak to it quickly as well?
Yeah, sure thing. So there's a lot of nuance to this. I've written extensively about kind of ML ops and then how data plays into this, as well as kind of the marriage of code and data, because there's some interesting symbiotic relationships between them when it comes to machine learning. So yeah, typically how I think about it is that there's these two loops in machine learning, and you have your code aspect and then you have your data aspect, and both of these are they're dynamic. Both of these are changing pretty consistently over time, at least in production machine learning cases. And so managing those can get really interesting. So for instance, the data is quite big, whereas code is much smaller in comparison. So you kind of need to use different tools to manage these two things. Git and GitHub and those tools for software, managing software releases and versioning and collaboration are excellent for that. But then once your data meets once your code meets your data, then you start to get some interesting situations, and managing that, in my opinion, is where Pachyderm comes in really strongly. You need something that has this scalable data layer, but then also is able to run these pipelines in a reliable and consistent way.
If I may add to that, Jimmy, it's sort of one of those problems that you never knew you had until you run, face first into a brick wall. It is also one of those things that are relatively easy to talk about, right? Oh, it seems so logical, but when you actually want to implement it, it is really, really hard. And much harder than you might think on first try. And that is something where, as Jimmy said, there's more layers. The more you get closer to production environments, and the further you start to scale out, you suddenly run into problems you didn't know you had before. And that is where, Pachyderm and team are way ahead of the curve in solving those things. And it's really a joy to see how something that you couldn't get running at some point now runs effortlessly because somebody else thought about how to put those things together.
Very well said.
So this, if I may, Moira, because this goes into John Blishak's question about the idea of Git for data. And Jimmy, it's a question that I've tried to answer. So the question is, okay, if this is Git for data, does it get to be storage intensive? And I think the question, or my answer has been before, correct me if I'm wrong, yes, but it's worth it.
Yeah, I think that's right. So I would say even Git for data, it's almost going the direction of GitHub for data. Is like once we start thinking about it from a system kind of standpoint, because you do want you typically do want to be able to go back in time on any one of your Git repositories in GitHub, or even other Git repositories. So yes, the storage can start to get a bit intensive. There are ways if you want to, I mean, sometimes regulatory reasons, you need to purge data from before a certain time or these kinds of things. And so we do allow that. You can also do exports, and then kind of what databases do, you can do snapshots and then store those to disk where it's less intensive, but or compress that down and do whatever you would like to do. But it definitely can. I think you're right, though. It is worth it. I'm thinking about all the issues I've run into productionizing machine learning, well, in particular on speech recognition, and knowing, oh, which data set was this model trained on, and needing to go back in time and figure that out. And some of the difficulties I've run in prior to Pachyderm, at least there.
Jimmy, can we do as John suggests, that we start to rotate, that we say anything older than 15 days or 60 runs, delete it for me?
Yes, you definitely can. So I would have to look at the exact details because I haven't done one of these pipelines myself recently, but yes, so you can set certain I'm forgetting the exact name of them, but certain parameters where you'll archive or purge data that's older than a certain amount, or only retain the most recent X amount of data from whatever time inside of memory. Or sorry, inside of the object store.
Cool. Moira, I put up the thank you screen because I think we're running to the end. You know, we're almost at the top of the hour. So thank you, Moira and Jamie, for giving me the chance to talk about this, and everybody here for listening to me talk. Yes, the code will be uploaded, and we will be happy to include the slides there as well, Alpha. Yeah, there's one question. I thought somewhere, what is the best way to start working with this? In my experience, the Pachyderm documentation. So there's some really fun experiments using different models, Python code, stuff in the tutorials. And going through those tutorials is a great way to start. Doing it on Pachyderm Hub means that you can start very quickly. So my recommendation would be to start there.
Yeah, that's a great answer. And I would also just add to that we have some links up here on the slide. Pachyderm Hub is our hosted version. So if you don't already have your own instance of Kubernetes, it allows you to instantly spin up clusters using Pachyderm Hub. And then we also have new enterprise trials. And then, of course, we have our open source version as well. So there's many ways to get started with Pachyderm based on your current infrastructure and your needs. But of course, if you have any questions, you can reach out to info@pachyderm.io, and we'd be happy to answer your questions for you and help you. And then, of course, we work with ixpantia and Franz's team, who are Pachyderm experts and data science experts in general. So they're a great resource for you to help you ramp up and get started, or if you want to evaluate anything, any use cases. And just to answer Alpha's question a little bit more, we'll send out where the presentation and the video will be posted after this, so we can definitely share that all with you. All right, thank you so much, everyone.
Thank you.
And
Bye-bye.